Okay, so in this video, I'll explain what SVD is, and yeah, I'll explain what SVD is and why do we use it. And I'll also give an example. In this video, I won't give a full example. I'll just give the steps that you have to follow to solve for SVD. In the next video, I'll do a full example from scratch, step by step. So SVD basically stands for singular value decomposition. Okay. So what does that mean? Basically, SVD is a method to factorize a matrix of any dimension, any rectangular matrix. Let's call this a matrix of dimension m into n. According to SVD, any rectangular matrix on the planet, in the universe, anywhere, can be factorized into three parts. The first part is U of dimension m into m. The second part is sigma of dimension m into n. The third part is V transpose of dimension n into n. All right. So now let's understand what U, sigma, and V transpose are. Sigma is basically a diagonal matrix. Okay. And this diagonal matrix sigma contains singular values of the matrix A. Contains singular values of the matrix A. Okay. What are singular values? Singular values, let's say sigma is my singular values, is roughly equal to the square root of the eigenvalues. Okay. So singular values of A will be roughly equal to the eigenvalues of A. Okay. Um, so this is singular value. So sigma is a diagonal matrix and it contains only the singular values. M into M is basically an orthogonal matrix. Okay, it's an orthogonal matrix. And this is also called the left singular matrix. Left singular matrix. It's just a terminology, that's what it's called. What this basically has is that the ith column of U is basically the ith eigenvector of A transpose. Okay. Similarly, V transpose n into n is also an orthogonal matrix. It's also called the right singular matrix. Take a guess why, because it's on the right of sigma. And the ith column of V transpose is the ith eigenvector of A transpose A. Okay, this is similar to what we get as a final result of PCA. In a lot of ways, PCA is a very, very special situation of the SVD. It's a very special case of the SVD PCA. So if you want to understand what PCA is, just go to my PCA video. I've explained PCA using the variance maximization method. In the class, we were explained with the error minimization method. You can do either way. I've explained it using the variance maximization method. And I plan to make a video on error minimization later on. But for now, just remember this. These are definitions and you just need to remember them. So next, let's understand what orthogonality is. Okay, orthogonality basically means that if I have two vectors and I multiply them with dimensions, let's say I have 2 comma 1 comma minus 2 comma 4, and multiply this with another vector 3 comma minus 6 comma 4 comma 2. uh, if these are all dimensions. This is the first dimension, this is the second one, this is the third one, this is the fourth one. The dot product of this, which is basically 2 into 3 plus 1 into minus 6 plus minus 2 into 4 plus 4 into 2, this is equal to 0. That's what orthogonality is. So when it comes to matrices, if A transpose A is equal to A transpose is equal to I, then the matrix is said to be orthogonal. Okay, what does this mean? If I have A transpose A as a vector, sorry, as a matrix, what this means is that if I take the first row, sorry, the first column, and I multiply it with the first row, the multiplication of this will be 0. Similarly, if I take the second column and I multiply it with the second row, the multiplication of this will be 0. This is A transpose A or A transpose. If as long as A transpose is equal to A inverse, as long as this condition is satisfied, this will always happen. Okay, that's orthogonality. Now let's understand what a normal vector is. A normal vector is basically a vector of unit length 1. Okay, so if I have a vector, let's say v dash equal to 2 comma 4 comma 1 comma 2, so basically the magnitude of this is 2 square plus 4 square plus 1 square plus 2 square under root. This is the magnitude of this vector, right? So the normalized vector will be equal to 2 by, this is equal to 5, I guess. Yeah. So if you calculate this, the magnitude is 5. 2 by 5, 4 by 5, 1 by 5, and 2 by 5. This is a normal vector. Okay, so a normal vector is basically a vector of unit length 1. And any vector can be normalized to a normal vector. You just have to divide every dimension of that vector with its magnitude. That's how you normalize a vector. So this becomes a vector of unit length 1. We generally do this to make calculations easier. Yeah. Then there is an ortho. So then after this, there's something called an orthonormal vector. What is an orthonormal vector? Take a guess. Vectors of unit length 1 which are perpendicular to each other. So they are normal because they are vectors of unit length 1 and they are ortho because they are perpendicular to each other. So if I have u1 and u2, and if the magnitude of u1 is 1 and the magnitude of u2 is 1, and if I take the dot product u1 dot u2, I will get, what will I get? I'll get 0 because that's what orthogonality is, right? This is what orthogonality is. So that's an orthonormal vector. So now that we have done that, let's understand something called the Gram-Schmidt process. Orthonormalization process. Okay. So what is the Gram-Schmidt orthonormalization process? It's just a method of converting a set of vectors, a method to convert a set of vectors into a set of orthonormal vectors. Okay. So now to find the SVD or to find the factors of a matrix, there are lots of methods. So you can use row echelon form using Gaussian elimination. This was taught in class. Echelon, I think that's how it's spelled. Uh, you can also you can also solve them by solving a system of linear equations. Equations. You can solve a system of linear equations and get the final value of SVD. Or you can use the Gram-Schmidt orthonormalization process, which is the one that I'll be using. So I generally use Gram-Schmidt because it's very procedural. There's not a lot of thinking involved. It involves a lot of calculations, but uh, it's procedural. It's very deterministic. You don't have to do anything else if you know the formula. Although the drawback of GSOP is that it can get a little messy if the matrix, especially if the matrix is big. But if the matrix is small, GSOP is a very good way to do that. Row echelon form, I don't like it because it requires a lot of trial and error, right? You have to first convert your matrix into a reduced form using Gaussian elimination, and Gaussian elimination involves a lot of trial and error. You have to see what row to subtract from which one and all of that. And linear equations, I don't know why anyone would want to do this. This is so long. So I follow GSOP. There are at least 10 different methods to do this. You can follow anything you like, but for all practical purposes, I'll be explaining GSOP. Okay. Yeah, I'll be using GSOP. I'll call it GSOP from now on. Gram-Schmidt orthonormalization process. So let's say I have a vector, a matrix A, all right, and the matrix is 1, 0, 2, 1, 2, 2, 3, 1, 1, 0, 1, 0. Okay. I'll call each one of these. So a matrix is basically a set of vectors, right? It's a set of vectors because this is one vector, this is the second one, this is the third one. I'll call this vector v1, I'll call this vector v2, and I'll call this vector v3. Now I want to convert this into an orthonormal matrix, okay, because I have to convert a set of vectors into a set of orthonormal vectors. Okay, I have this, I'll call this AO, which is a set of orthonormal vectors, and I want U1, U2, and U3, which are all orthonormal. And this is used in SVD, so I'll explain this method now. First, I'll tell the formula, and I'll then tell you how to follow that formula. So W2 is given by, not W2, WK. WK is given by VK minus sigma I equals 1 to k minus 1 ui dot vk into ui. Okay, and basically the u vector over here is w in normalized form. Okay, you'll understand what I mean when I do the example, but this u1 is basically w1 normalized. Okay, u2 is w2 when you find w2 normalized, and u3 is w3 when you find w3 normalized. Okay, so when I want to find w1 is v1 minus this I equals 1 to 0 ui u1 into v1 into u1. But because this goes from 1 to 0, in the first iteration, I cannot do this. So this is just 0. So the first iteration, w1 will only be equal to v1, okay? Which basically means that it's equal to 1, 0, 2, 1, right? Now I told you that u1, which is the set of orthonormal, which is one vector from this set of orthonormal vectors, is basically w1 normalized. So I'm going to normalize w1. w1 normalized is basically, take the magnitude of this. This is basically 1 square plus 0 square plus 2 square plus 1 square. That's under root 6. And divide every vector over here, sorry, every value in this vector, every dimension in this vector with root 6. So I get 1 by under root 6, 0, 2 by under root 6, and 1 by under root 6. Okay. So this is my first vector over here. 1 by under root 6, 0, 2 by under root 6, and 1 by under root 6. Okay. Now I have to find W2 using the same formula. W2 is basically equal to V2 minus sigma I equals 1 to 2 minus 1, because look, K over here is 2, right? This is the main formula. K over here in this second iteration is 2. So 2 minus 1. Ui is 1. In the first iteration, it's 1. Okay. u1 into v2 into u1. Okay. So this is basically W2 equals V2. What is V2? V2 is 2231, right? 2231 minus, what is U1? U1 is this normalized vector that we found. It's 1 by under root 6, 0, 2 by under root 6, 1 by under root 6. Dot product with v2. v2 is again 2, 2, 3, 1 into, this is a scalar multiplication, okay? Into u1, which is again 1 by under root 6, 0, 2 by under root 6, and 1 by under root 6. Okay? That's the scalar multiplication. So when I solve this, I'll basically get W2 equals 2, 2, 3, 1 minus this basically comes out to be, hold on, 2 into 2 by under root 6 into 0 plus 2 plus, so this is 2 by under root 6, 0, 6 by under root 6, 1 by under root 6. Okay, I've just done a scalar multiplication. Yeah. So now when I square it and I add it, I get, what do I get? I get, oh wait, sorry, I made a small mistake. This won't be a vector, it's a dot product. So basically I have to multiply the dimensions and I add them. I multiply the first dimension with the first one, this with this. So basically this is 2 into 1 by under root 6 plus 0 into 2 plus 2 by under root 6 into 3 plus 1 by under root 6 into 1. And then this is basically a scalar. So that will be multiplied to 1 by under root 6, comma 0, comma 2 by under root 6, comma 1 by under root 6. Okay. So this is basically W2 equal to 2, comma 2, comma 3, comma 1 minus, this is 6 plus 2, 8 plus 1, 9 by under root 6 into 1 by under root 6, comma 0, comma 2 by under root 6, comma 1 by under root 6. Okay. Now this is scalar multiplication. So I have W2 equals 2, comma 2, comma 3, comma 1 minus 9 into 1 by under root 6. So that is 9 by 6. Then the second one is 0. Then it's 9 into 2 by under root 6. So that's 18 by 6, which is 3. And nine into, yeah, that's again 9 by 6. So when you subtract this, 2 minus 9 by 6, which is 3 by 2 minus 3 by 2, and all of that, you'll get W2 equal to half, comma 2, comma 0, comma minus half. Okay, that is your W2. So now you have to find, so this is W2. Okay, now U2 will be the normalized value of W2. So W2 normalized is basically equal to, what you have to do is, you first have to find the magnitude of this. So that's 1 by 4 plus 4 plus 0 plus 1 by 4, and you have to find the under root. That's 16 by 4, so 18 by 4, which is basically 9 under root 2 by 2, right? This is basically 9 by under root 2. Okay, so now when I have that, I'll basically divide half by 9 upon under root 2, comma 2 upon 9 upon under root 2, comma 0 by 9 upon under root 2, comma minus half upon 9 by under root 2. Okay, so this basically gives me W2 n as, oh wait, I just realized my mistake. This will be 3, not 9, because it's 9 into 2 by 4, right? So that's 3 by under root 2. This is 3, so I have to divide it by 3 everywhere. Okay, that's 3 by under root 2, and yeah, so when you do that, you basically get the normalized value of W2 as under root 2 by 6, under root 2 by 6, comma under root 2 by 2 under root 2 by 3, comma 0, comma minus under root 2 by 6. Okay, so this is the value of the second vector, under root 2 by 6, 2 under root 2 by 3, 0, and minus under root 2 by 3. Let me just check my notes if what I've written is correct. Yeah, 6 minus under root 2 was 6 apparently. Yeah. Okay, so this is the value of u2. Okay, so now when you have to find w3, which is the last value of, which is the last vector, what you do is you basically w3, if you take the formula, w3 will be equal to v3 minus u1 dot v3 into u1 minus u2 dot v3 into u2. Okay, you have u1 and u2 from the matrices that you found, so from the vectors that you found. v3 is your v3 over here. This is your v3, and now you have to solve this. So after you get w3, don't forget to normalize it. Okay, you have to normalize it, and when you do that, you'll get the final answer as 2 by 3 comma minus 1 by 3 comma 0 comma minus 2 by 3. Okay, minus 2. So I'll leave this calculation to you. If you don't understand, just let me know and I'll write the calculation again. But it's very simple. You just literally multiply, subtract, multiply, subtract. So yeah, I'll stop here. And now I'll just explain SVD with an example.